This meeting is being recorded.
Should I start, Beth?
Yes.
Yeah, good morning and good evening to all my friends in India and the US. I'm Professor Gautam Datta, retired faculty of IIM Ahmedabad, and we are doing jointly with Informs the webinar series on applied analytics. So with me, we have panelist Dr. Rajesh Tyagi. Then we have Professor Sachin Pattabardhan, Dr. Jose Korak from Tata Steel. Sachin Pattabardhan is from IIT Bombay, and Sanjay from IBM. Before I start, I just want to hand over to Rajesh. He will speak about the info section on practice, and then I will talk about the initiatives what ORSI has taken. So over to Rajesh. Yeah, Rajesh.
Hey, thank you, Gautam. And again, Gautam and thank you to Gautam and Sundaravali because they have been instrumental in starting this whole series of webinars from India, which essentially targets Indian audience. And I know Gautam will talk a little bit about that. But I just want to talk about Inform section. So I'm Rajesh Tyagi. I'm the president of Inform section on practice. Inform, for those who are not familiar, is basically the Institute for Operations Research and Management Science. And the section on practice, or the practice section, essentially it's a special interest group within that Informs community, which supports the practice of analytics and operations research and management science. So essentially, folks who are practitioners, we try to figure out how we can help them network, address any questions they might have. And typically they range in terms of, hey, look, what kind of problems other people are solving and what kind of toolkits other folks are using. So to that end, we have three major annual competitions. And again, I'm not going to go talk through each one of them, but these are the three major Informs level competitions. And the practice section is honored to be given the responsibility to run those competitions. We also have some periodic or somewhat monthly events. We have these applied analytics success series webinars, like this one that we are talking about. We also have a virtual happy hour. And like I said, Gautam has a few more planned next year. And I have reached out to some folks, one of my colleagues at GE India Tech Center in Bangalore, and they are going to come up with a few webinars as well. And also, I want to mention that starting next year, we are going to have a special series on generative AI, and that should be a very interesting webinar series. And again, go to the practice section webpage where you registered for it. There is a tab there for virtual happy hour, upcoming webinars, and again, you can find some of those information there. And I will announce it via some of those emails as well. So if you are signed up for this webinar, you will get some reminders from me when those webinars take place. So I'm going to stop here, and there is a very nice presentation that we'll have from Tata Steel, and back to you, Gautam.
Yeah, thank you, Rajesh. So I'll just talk about that initiative we have taken. A few years back, Rajesh and I was discussing why actually we are not getting, Rajesh was chairing the Edelman Award in the Informs, and I was a member of the team which selects that Edelman Award. So then we figured it out that not enough entries are coming from India. And the question is that why India is so less represented. So we actually thought about doing two things. One is that webinar series like the series which we are actually having now, I think invite people who are doing practice to share this in a common platform through a webinar, which Informs is hosting. And we are actually, I am representing here the ORSI site, and Rajesh is representing Informs site, although I am a member of Informs also. And in my team, we have several people like Sanjay from IBM, Dr. Sengupta from TCS, Professor Basu from IIM Bangalore, Goda Ramkumar and the Swiki, Sundaravali from IIMA, and Sumita. So what we have done is that with this core team, we have decided to launch a national practice prize competition. And this year, we had about 15 entries which actually were there. We have selected 5 of them, and we are going to announce them in the open platform in a few days from now, that who others been selected. 5 prize selection, first prize selection will happen through a presentation, physical presentation at IMA in 12th of January. And we will be in future competition 25, 26. We'll be looking for more entries. We'd like to really see that practice actually coming up the same way practices come in the USA, because India is a big economy and we can expect India to grow. At the same time, we can expect that practice of analytics and management size is increasing. Okay, so I'm now going to hand over to the presenter today. We have Dr. Jose Horath, who is the Chief of Intelligent Systems and Mathematical Modeling at Tata Steel at Jamshedpur, and he's also used to be a head of automations. He has, other than Tata Steel, close to 20 years. He has about 4 years experience in sale. He is a metallurgy from Indian Institute of Science, ME in metallurgy, and University of Sydney, PhD. So we are going to listen to him, and with him, he is co-author, Dr. Sachin Pattabardhan, who has degrees from IIT BHU, MTech in chemical engineering from IIT Madras, and PhD from IIT Bombay. He's a fellow of Indian National Academy of Engineering, visiting professor in Carnegie Mellon Technical University in Mulsanne, and he is also been chair professor at IIT Bombay. With this, I'm going to now stop sharing and give the presentation to the Professor Pattabardhan and Dr. Korath, who will be taking the session. And at the end of this, we will have question and answer. But first, we are going to answer those questions which are going to come from the chat boxes or the Q&A written questions. And then I think open questions will be provided. So then we're going to open this. Over to Dr. Korath and Professor Pattabardhan.
Thank you, Professor Datta. So I'm just,
yes.
I think I can share. So it's not.
Yes.
Is my screen visible?
Yes, screen is visible to me, at least.
Yeah,
it's visible.
Yeah. So good evening and good morning, everyone, and welcome to this presentation on optimization of continuous steel annealing operations using model predictive control. With me is I'm Jose Korath from Tata Steel, and with me is Professor Sachin Pattabardhan. We'll start with a brief introduction of the Tata Group and Tata Steel and the business context within which we operate. Also, the strategic significance of automotive steel market segment. Then we'll go to the project details. So about Tata Steel, is part of the Tata Groups, one of the most diversified groups in the world and most well-trusted group, with an annual revenue of about 150 billion US dollars. And we have about 30 listed companies and many other non-listed small companies. These are the key group companies: Tata Consultancy, Tata Steel, Tata Motors, Titan, and Air India. Tata Steel is the flagship company of Tata Group, and it was established in 1907 in India. So now we have operations in India, UK, Europe, mainland Europe, and Americas, and also in the Far East in Thailand. In India, we have got 5 integrated steel plant facilities. And here we are a mine-to-market steel major, having the entire value chain starting from mining to finished product. So if you look at the steel industry in India, as we know, Indian economy is growing rapidly, and is primarily by the powered by the growth in infrastructure projects and the other aspects of urbanization like automotive, housing, etc. So this is a big opportunity for consumption of steel, and it is estimated that by FY30, the Indian steel demand will double to almost 300 million ton per annum. So the Tata Steel is also planning to, capitalize this opportunity, and we are our plan to double our capacity in the coming 5 years. By FY30, we'll become 40 million ton in India from current 20 million ton. That plan is under execution. So that is a overall broad context. And if we come to automotive steel, so among the steel market segments, the most premium one is automotive. At the same time, it is the most competitive and with a very, very well established and stringent global standards for its quality and supply chain requirements. See, most of the steel used in automotive is cold rolled and annealed. If you take a car, typically 60% of the components are made of cold rolled and annealed steel. And so it's needless to say that the quality of the steel is very important for the safety and durability of the car. So that is a context in which this project assumes significance. Okay, so so we have tried to optimize the annealing operation in an integrated steel plant. So the objective is that to get smart decision-making solution for a annealing line, so that the product which comes out with consistent quality and in a fuel efficient, in a cost-effective manner. So this has been implemented in the most value-adding plant of Tata Steel India, and the quality improvement what we got is remarkable, and it had been a very big, great change management story as well. So before I get into the project details, to familiarize the audience with the steel manufacturing process, we have prepared a 2.5 minute video. I would request you to go through this.
Let us understand the various steps in Tata Steel's integrated steel making operations. A mining-to-market steel company, Tata Steel's value chain begins at its captive iron ore and coal mines with the extraction and preparation of iron ore and clean coal. Inbound logistics transports raw materials from different locations to the steel works. Coal is converted into metallurgical coke and iron ore into pellets and sinter before they are charged into blast furnaces. Hot air reduces the raw materials into molten iron, while impurities called slag float to the top. The hot metal is collected in a torpedo which transports it to the steel-making shop. Here, it is tipped into a transfer ladle, which carries the hot metal to the steel converter. In the converter vessel, high-purity oxygen is injected via a lance to refine the hot metal into steel. Liquid steel is then transferred for casting into solidified slabs, cut to the required length and sent for hot rolling. After being reheated, the slabs are rolled into the required length, width and thickness as per the production schedule. The hot rolled strip is then passed under laminar cooling to achieve the desired mechanical properties. Thereafter, this strip is further wound into coils of almost 1 kilometer length. It is then strapped and marked for the customer before being sent to the coil yard for dispatch. Steel for automotive applications is sent to the cold rolling mill for value addition. Here, hot rolled coils are pickled and rolled to create cold rolled sheets, which make the steel hard and brittle. To make automotive steel ductile and formable, it must undergo reheating in a process called annealing. The focus of the current project is on this annealing process. At the continuous annealing line, successive coils are continuously welded to maintain continuity across the line. Steel coils are then endlessly fed into the continuous annealing line. In the annealing furnace, the steel strip is reheated to a target strip temperature to allow the strip to regain mechanical properties that make it ductile and formable. After the annealing process, cold rolled sheet is galvanized in a zinc bath to provide protective coating against corrosion and acquire surface finish. Every inch of strip surface is inspected and tested for the desired mechanical properties. At the delivery end of the line, finished strips are wound into coils, packed and strapped with the help of robotic machines. Packed coils are stored in yard and dispatched by road and rail as per production plan.
Yeah, as you would have seen in the video clip, the manufacturing supply chain of an integrated steel plant is, yeah. So as you have seen in the video clip, the supply chain of an integrated steelworks is fairly complex, given the variety in the physical and chemical and thermal processes involved, apart from the enormity of the logistic operation. This slide captures it, schematically. So we have a huge product basket, starting with, same liquid hot metal. We make about 300 grades of uh, steel slabs, and from there about 800 grades of hot rolled products. And from that hot rolled coils, some part goes into market, which since they find direct application, and the remaining some part go to cold rolling and annealing line. There in cold roll and annealing segment itself, we have about 11,000 SKUs. So the what we say, with such a macro and micro level complexity in the supply chain, to meet on-time delivery commitment to our customers, we use a very well-established, robust, at the same time flexible framework for production planning and through the value chain. Okay, so we use advanced SCM platforms like BY etc. to have the production planning. That is the first level of decision making. Second level of decision making need to happen at individual unit process, whether it is steel making, rolling, casting, or annealing. So that also equally that needs to take care of the specificities, the constraints of that particular unit operation. Here in this project, we developed an optimization solution for the highly value-adding finishing operation called continuous annealing, which is very critical to quality, especially for the premium automotive steel segment. Let me use a pointer first. Okay. So we'll just go to the problem. So why, annealing is required? When we cold roll the steel, so the steel greens, basically we are reducing the thickness of the steel by applying pressure, applying force. So that leads to the rupture of the internal grains, the crystals of the steel, and the deformed structure will have a lot of internal stresses generated in it, and it makes it in a way brittle. So with that brittle steel, we cannot give any forming. We cannot do any forming application. We cannot make any shapes with any shapes by forming operation. So in order to recover that formability or the ductility of the steel, we need to subject it to a process called annealing, where something called recrystallization happens, where we have the stress-free equiaxed grains taking a kind of rebirth from the deformed structure. So this is achieved, this annealing, essentially it is heating the steel to a particular target temperature where this recrystallization happens. So there are many technologies for, annealing, batch annealing, etc. But the most modern one is the continuous annealing line, especially for producing premium steels used for automotive applications. Now, this is a schematic of the continuous annealing line. Typically, the CAL consists of a number of unit operations which are connected and operated in tandem. The steel coils are unwound and fed continuously to the line, one after the other, with the tail of one coil getting welded to the head of the next coil. It passes through a surface cleaning unit first and then enters the furnace where it gets annealed. It is followed by post-processing like metal coating that is optional. Some lines do not have a zinc coating. Then a single stand rolling which gives a mild elongation and get wound on a winding reel and ready to dispatch. So if you look at the, I'll just before this. If you look at the this line, there are two things we need to keep in mind. One is the tightly coupled nature of the line. That means the disturbance in one unit can easily lead to a disturbance in the other, kind of domino effect. Other aspect is, the the varying scales of dynamics of different units. The some of the units are very quick to react. For example, the rolling mill. If we apply if I apply a change in the set point, it will react very quickly. Whereas a unit like furnace, which is having very high thermal inertia, is very slow in response. So this different in the variety, the variability in scale, that also poses a challenge in controlling the line in a smooth manner. Controlling the connected line, I would say rather. Okay, to just get this being a schematic, just to get a feel how the line looks like. It's a small animation we have made. You can see the uncoilers, coils getting unwound and entering the furnace, then the coating line. It goes through different storage buffers and it get finally wound off. So this is always in motion. At a steady state, it will look like this and continuously being fed from the entry side. So let us have a look at the, a closer look at the annealing furnace. That is a place where that is a unit where we are applying our, our optimization solution. So this just have a look at the anatomy, the scale and complexity of the furnace. Furnace is nothing but a rectangular heating chamber with the temperatures increasing along the length. A steel strip passes through the furnace, and as it passes through, it gets gradually heated up to a specified target temperature. The basic heating element inside the furnace is the radiant tube, which have been shown as this, this red boxes, and it's blown up here too. This is a structure of a radiant tube. And the gaseous fuel burns inside this radiant tube. And that in turn heats the radiant tube surface. And the heat radiates from the surface to heat up the furnace ambience, and the strip get indirectly heated up. Why do we adopt such a methodology? Is an open flame will contaminate the steel surface. This one will prevent that contamination. So it is an indirect heating. So how do we these radiant tubes, we have about 100 plus 150 plus radiant tubes inside the furnace. These radiant tubes are grouped into different zones for the purpose of controlling the furnace temperature profile. By regulating the fuel flow into the radiant tubes in each zone, we can control the temperatures in each furnace zone, which in turn will have its effect on the strip temperature. So operator gives the desired temperature set point for each zone, and lower level controllers regulates the fuel flow accordingly. Regarding the scale, at any given moment, there are about few hundred meters of strip length passing through the furnace, but they are in motion. Typically, a strip takes about 3 to 3.5 minutes to pass through the furnace. The most critical aspect of the furnace operation is that temperature of the furnace zones need to be set in a coordinated fashion. This real-time decision making under dynamic operating condition is what ensures optimality of the annealing process. Now, the problem where the suboptimality arises from. The first problem I saw, we saw the slide depicting the complex supply chain. We saw that the wide variety of products we make through the same line, which means we will have lot of transitions, coil after the coil, which comes to annealing line will not be of the same type. Given the, delivery requirements, we will be having lot of variation transitions as part of the daily planning. So it's an intrinsic characteristic of the supply chain. The second one is the operational challenges from the shop floor, the plant disturbances. The first one, again, I'm just repeating. So we will have a situation when we have the leading coil is having a target temperature of 800 degree to be met once it passes through the furnace. Whereas the trailing coil has got a target temperature of 700 degree, because that is a grade of that is a temperature demanded by that particular grade for it to achieve the recrystallization. Excuse me. So, this transition, so we need to manage this transition without, over annealing or under annealing inside as they pass through the furnace. So this requires dynamic management of the furnace temperature profile so that leading and trailing strips are heated correctly and meet their respective target annealing temperatures with minimal deviation during the transition. See, there will be some, given the furnace inertia, there will be some underheating or overheating, but how well we can minimize it with a smart decision tool. That is a challenge. So this is just showing how the welding is happening one after the heads and tails. So this is the other problem. Suppose there was some problem in the welder. The welding, which is supposed to finish in say 30 seconds, took say slightly higher time, 45 seconds or 50 seconds. Soon that impact will be left in the felt in the furnace, because furnace will coil with we have to stop the line while welding is happening. The coil in the furnace will get overheated. So this kind of scenarios, the furnace need to respond with adjustment of the temperature profile to reject these kind of disturbances most effectively. So normally, I mean, for the past 20 years, whatever we can say, this is being done by the operator at desk. So his wisdom, his experience, his skill comes into play. So, and it's or some of the times this both grade transition and the line disturbance happens together. So it's a it's a very, what we say, this legacy practice of adjusting manually is result in suboptimal decision. Then normally, so for example, you can see a typical case, the operator will be responding to different calls from entry side, exit side, and he will be adjusting the set point. So there is a lot of room for getting panicky for an average operator on a daily basis. So this legacy practice to handle both problem scenarios mentioned above was to adjust furnace operation set point manually. Okay. So what is the impact of this manual operation? Okay, we salvage the scenario, but what is how severe this suboptimality is? So one is improper heating of the strip. As I said, either overheating. So in this case, as a picture shows, the leading coil is 800 and trailing coil is 700. So there is good chance of overheating of the trailing coil, which in turn will lead to over softness and more fuel consumption. Here it is a case of, if I try to reduce that, there is a chance of bring down the furnace temperature early. There is a chance that the leading coil get underheated, which will affect its mechanical property. Or if there is a speed reduction all of a sudden, as we shown here, so this part of the coil may get, overheated. So the purpose of the project is to see how much we can reduce this under annealing or over annealing, minimize this deviation. That is a objective of the, of the solution. So how it impacts on the quality. So this is the normal, every element of the strip is supposed to anneal within this temperature. If that doesn't happen, then there will be under annealing. And there will be, the mechanical property will be outside the band. If it is properly annealed, you will have the good mechanical property assured. Same is the case of over annealing. You will have too low, say, mechanical strength or something like that. So if the impact on product quality, either we'll have to reject it, or if it is non-uniform while product application, we will face difficulties. And even suppose we are able to manage the product forming, while it is in service, it will give trouble. So here it's it's illustrated with a sample, an example. So here under annealed hard metal, when it is subjected to forming, it cracks. And here a over annealed soft metal, when it is subjected to forming, it generates a lot of wrinkles. Whereas this one, it is just, optimal. So if you don't have this is no wrinkles, the intricate shape has been formed very well. So if a component with made of poor quality steel goes into service, and in the unfortunate incident of some accident or something, these components will fail and leading to very disastrous results. Other thing is, whenever this manual operation is done, operator tend to overreact, which invariably result in more fuel consumption and subsequent CO2 emission. These are the two impacts. So let's hear from our the problem is to solve. Problem to solve is that suboptimal decision making should be avoided. Okay, and what is the pain that plant manager have? Let's hear from the chief of the plant and head operation. It's Mr. Ajay Jha.
On any single day, our continuous annealing line, which has many interconnected units and different dynamics, caters to a production schedule comprising of the different grades of the steel, being fed to it continuously. In the past, any upstream or downstream disruptions in the line, besides schedule change in the steel grade of materials, was managed manually or by our highly skilled operators. The high thermal inertia of the annealing furnace made such transition management extremely challenging for them.
Among the operating crew, knowledge and skill level vary from operator to operator. This gets reflected in their handling of difficult situations, which are anyhow unavoidable during the line operation. So, a solution can give most optimal decision under all operating scenarios is what we wanted. That will enable every operator to maintain a consistent control of strip temperature and prevent strip quality degradation.
Have a solution which will come out with timely, automated, optimal set point decision at all times to ensure that the furnace operate at peak of its performance with respect to product quality, yield, and fuel consumption. More importantly, the solution must be able to handle the complexities of a multi-parameter system with a robust mathematical approach and efficient computability for real-time implementation. So we decided to develop an in-house solution based on model predictive control methodology and roped in IIT Bombay with Professor Padwardhan as our consultant. So now I will request Professor Padwardhan to share us with the solution strategy. Over to you, Professor. I will change the slides for you.
Okay, sure. So next slide, please. Yeah, so here we are trying to illustrate graphically what it means to manage a furnace. Managing a furnace operation is like moving an elephant. So there are constraints like you can't pull it too hard or move it too fast. So operator changing a set point is often like pulling the elephant in different directions without any coordination. So the problem is that the furnace has large thermal inertia, and to make optimal decisions, it is necessary to model the relationship between the thermal transients and the set point changes. Also, constraints on the furnace operation need to be honored while orchestrating these maneuvers. So, model predictive control is a technology designed to achieve such coordinated transitions under constraints. Yeah, so, next slide, please. Yeah, so model predictive control is a technology which is by now very mature, about 30 years. It's being implemented in the industry. It's a philosophy which is not very new to us. If you reflect on how you drive a car, then you will realize that you have a model for the transient behavior of the car in your brain. You use this model to forecast the implications of your decisions on changing accelerator, brake, and steering on the future behavior of the car over, say, horizon of next 5 seconds. And we continuously keep forecasting. This continuous forecasting over a future horizon forms the basis of our instantaneous decisions to manage lane driving constraints, road condition disturbances, or you target route following maneuvering. So we all use this model predictive control without even knowing that we are doing this. Next slide, please. So we decided to adopt this MPC philosophy for managing the annealing furnace operation. A furnace transient behavior model relating the zone target set points with the strip temperature was developed and stored in a control computer. This model uses repeatedly online to forecast over a horizon of next 40 to 60 minutes. So model is used to foresee what is going to happen if we make certain actions now, to assess possible consequences of the actions planned to manage the steel grade transitions and reject the disturbances due to steel mass flow rate changes. Now, the target temperature manipulations are chosen optimally such that a desired strip temperature is achieved at the end of the strip while avoiding any possible constraint violations. So, these maneuvers have to be done such that temperature constraints on the strip are obeyed continuously as it happens. Next slide, please. Yeah, let me give you a little bit of flavor of the maths that goes behind this. A popular approach to develop a model is to capture transient behavior of the furnace is to use what are called as transfer function models. Each element in this matrix is a first or second order ordinary differential equation. What I'm showing you here is a matrix differential equation. And each of them are also have this element of time delay. So because this is a system which is distributed over space and time, so the model relates controlled output transients with the manipulated inputs and disturbance inputs. For the purpose of implementing MPC using control computer, this model is converted into what we call as a discrete time state transition model driven by external inputs. This is what is shown here on the right hand side, discrete time state transition model. So this model is used for actually formulating the control problem. So next slide, please. Yeah, so just to give you a flavor of optimal control that has been implemented here. So what we do is we solve a series of optimization problems online, one problem every 1 minute. So discrete time model is further used to formulate this optimal control problem over a moving time window in future. The optimization objective is to minimize the sum of the square root of errors between the model predictions and target strip temperature over a future horizon, and also try to penalize the rate of change of future inputs. So dynamic production model gives rise to equality constraints. So those are shown here, subject to these equality constraints. And future input mu's and rate of change of input is also bounded. So there are bound inputs. So this is a classical optimal control problem. And the outputs, future predicted outputs are also bounded between certain limits. So on the next slide, we show a kind of a graphical representation of what is happening. The concept of, so here we are at the current point and we are at the boundary of the past and the future. So we are trying to use the model to forecast the future online. The concept of optimal control using MPC is graphically illustrated in this slide. When strip temperature is close to the target, a typical operator strategy is to hold the input constant. However, this can result in large deviations from the target temperature and constraint violations into the future. On the other hand, MPC runs an optimization engine to bring the predicted strip temperature as close as possible to the target temperature, such that the predicted radiant tube temperature stay within the safety limits over a future window of next 60 minutes. We implement the first optimal set point change for a minute and again the repeat the optimization problem at the next sampling instant. So this is done in digital control framework. To achieve the optimal operation, one optimization problem is solved every 1 minute. So this is similar to driving a car using continuous forecasting. So forecasting made decisions are made every 1 minute, and this runs ad infinitum till we decide to stop the controller. Next slide, please. Now let me relate it to the economics of the system. So manual control typically results in significant variability. So what is shown here in the beginning up to 4,000 minutes is manual control, where you can see a lot of variability. What MPC achieves is significant reduction in the variance of the controlled output. Now it is well known that economic optimum typically lies at the constraint boundaries. This is coming from the OR literature. And operators do not take risk of operating a plant close to the constraint boundary. This is because of the variability. But due to reduction in the output variance, MPC allows shifting of the operation very close to the constraint boundary and thereby realizing the economic benefits. So MPC basically allows you to take the system very close to the economic optimum. That is the advantage of using MPC. Go to the next slide, please. Yeah, so what we had was a plan of action. As an academic partner, my task was to train Tata Steel team in in-house development and implementation of MPC. So these are very, very expensive softwares available from commercial vendors. Tata Steel decided to do an in-house development. We came up with a game plan. The very first step was pinching or exciting the furnace to generate data needed for dynamic model development. So these are data-driven models. Huge data is collected from the past and also by doing experiments. So the models identified from the perturbation data was then used to formulate the MPC schemes. All those transfer function and state space models were obtained from operating data. For the real-time implementation of the optimal control, we transformed it into a quadratic programming problem, and QP problem they are known to be very efficiently solved online. So Sujit Jagnade, a senior technologist from Tata Steel, and he was the lead engineer in this project, and he worked under Dr. Korath on implementation of this plan. So I now request Dr. Korath to continue and tell the story of development and implementation at the plant. Over to you, Dr. Korath.
Thank you. So, as Professor said, the capturing the transient data was, an important thing in model development. So, for that, we purposely perturb the temperature set points of the furnace, the so-called pinching, the phrase what Professor used, and recorded the responses in furnace as well as strip temperature, furnace temperature as well as strip temperature. This had to be done such that the data reveals the correlation between temperatures of different zones and that between strip exit temperature. If you speak from a plant operation person's perspective, this had been one of the most challenging aspects of the development journey, as perturbing a running plant in a premium product line is a very difficult proposition. Normally, the furnace is operated at 120% capacity, and the operators were quite reluctant to allow any perturbations. Thanks to the support of our line management, we were able to conduct several perturbation trials, although we often had to wait for suitable windows of operation. So this one, this graphs, as you can see, we are changing the set points, these red lines, and we are recording the strip temperature response and the furnace temperature response. So this basically tells the furnace set point. Once we change this perturbation signal, the fuel valve will be opened accordingly, and the furnace will get heated up, and subsequently it will be reflected on the strip temperature. So the models, it was a series of models. The first model is predicting the furnace temperatures from the set points given. That is a model one. From that, the strip temperatures were predicted. This is model two. So always it's a combination of models connecting furnace set points which is currently given manually to the predicted strip temperature. Then through the optimization, optimal set points were arrived at. So basically these two models are always invoked in sequentially to get to do the forecast and do the optimization. So as Professor said, we cast it as a constraint optimization problem. Cast it as a QP problem and solve using an efficient solver. So this is some results from the from the trial. After once we developed the model and deployed it, this is some of the representative results. Here you can see it's a duration starting from the middle of one shift and the middle of the next shift. Say morning 11 o'clock to evening 6 o'clock. So there are two great transition. First, we had the coil which is at target temperature around 710. Then the next, after an hour or so, another coil came with higher target. Then again the previous grade came, and after some time again there was a shoot up in target. The point to note
We
is
need to wrap up.
Yeah, I will
Another
take
5
another
minutes.
5
We need
minutes.
to wrap up. Yeah, give some time to the attendees to ask questions. Yeah, quickly. Take another 5 minutes.
There is a demand to change the temperature by 100 degree, 110 degree over a very short time window. So this was also coming along with the thickness change, the mass flow change, thickness and width. Okay, and the line speed was also changing depending on the dynamic conditions in the plant. So this is how the system tried to manage it. Since the MPC knows what is the next coil coming up, and it started raising the temperature so that this high grade coil reaches its target on time with some level of overheating of the leading coil. Similarly, as soon as the high temperature target coil passes, it immediately brings back the temperature of the furnace so that the coil with 700 degree centigrade is getting heated properly. Similarly, here also the set point action is taken well in advance, so that by the time we reach at say 5 o'clock in the evening, the furnace is heated up to give the right temperature to the high temperature coil. So this is how the furnace set points are varying. You can imagine never a manual strategy will allow us to do this kind of complex tracking and changing. It will be always a stepwise changing. Operator will change it and leave it for some time. So it will be always suboptimal. Whereas a system driven solution, an automatic solution, is managing it optimally. Coming to the implementation, of course, this we are implementing on top of a system, a control system, which is running there already. So the integration with the legacy system was very demanding. We need to know the interface should be properly taken care of, and the safety requirements, safety limits should be taken care of, and the engagement of the OEM of the legacy system was important, and the performance compatibility. Even the MPC system is able to compute fast. How fast the underlying below layer system will be able to respond. So these were some considerations. So if you look at currently, this is the automation architecture. The manual set points are given. The PID controllers control change the valve fuel flow rate through the valve control. What you have done is we have put MPC layer on another computer. Here the optimization runs, and the set points are given to, instead of manually giving, set points are flowing to the PLC from this level 2 computer. The legacy system was a Honeywell system. So the other important aspect of the change management, as I said in the beginning, for past 22 years, the people were operating this line manually. Okay, so introducing a new solution into a system was quite, it would naturally face with some resistance. So we tackled it in two ways. One is strategically. The MPC could have given the fuel flow rate directly and control the furnace. But we decided not to give the fuel flow rate, but rather calculate the set point and give it to the PLC system. Because then that is what operator had been doing. He gives the set point and he knows how the furnace behaves. So when MPC solution is giving the set points, operator will be able to calibrate, okay, how good or how bad it is, whether it is as per my expectation, so that acceptability will be more. So that was one of the decision we took. We will give the set points rather than directly controlling the fuel flow. Other thing was, whenever we introduce a new solution in a running plant, people often tend to introduce a new system, a new computer, new monitor, new screen to look at. So people are resistant to that. What we did was, the existing control system existing UI was modified with the help of the OEM supplier, and so that he can do it. He needs to look at on the same screen what he had been looking at all the time, all along. We gave a soft switch for the operator to switch back to manual mode and auto mode, so that in case if he's not comfortable with the solution set points from the MPC solution, he can take it manually. So these two things helped us in managing the change well. So after this, we started the trial first in a few minutes, then a few hours, few coils, then one shift, then few shifts. Then gradually we increased, and we took the feedback from the plant team, the operating team, incorporated their suggestions, did the necessary fine tuning. So by doing that, by end of January 2023, beginning of January 2023, MPC had become the normal by default operation mode. So you will see here these 2 months there was a line shutdown for some major revamp. So that is why you don't see here. Otherwise, on an average, it is used from 85, or sometime in some months it goes up to 95% usage. So this shows how the previously operator used to give the set points. Now MPC solution is giving the set points. So it's a closed loop control. There is no open loop here. So let's hear from the operating people. It's about a few seconds.
Since the solution has been integrated in our existing user interface, our attention is not divided across additional screens. Adoption of this solution has made operations much easier because it allows us to switch back to the manual mode when it is required. We are able to monitor multiple processes with much greater ease since the most critical process is being taken care of by the MPC solution.
अब टेंशन नहीं होता है जब ग्रेड चेंज आता है या लाइन स्लो डाउन करना पड़ता है। पहले तो हमें बहुत परेशानी होती थी, बट मॉडल आने के बाद काम करना बहुत आसान हो गया है।
At Tata Steel, any technological upgradation is seen as an opportunity for future rather than a threat for present employees. The technological upgradations lead to knowledge and skills enhancements, thereby creating opportunities to do more value-added jobs. The whole team gets motivated by the outcomes of the change management process, and they further look for opportunities in other processes to add more value with the new learnings. This creates a highly energized and engaged teams, which is the foundation of Tata Steel.
So coming quickly, this was
Okay.
the. Okay, I'll take 2 more minutes, Professor.
Okay, 2
So
more
this
minutes.
is the
Fine.
yeah, this is the biggest impact on quality, the temperature compliance. See, if you see, we allow any product any element of strip which is within plus or minus 15 degree band. Okay, but how good is the tighter control? So if you look at the closest band within plus or minus 5 degree, there is a remarkable improvement from 30 degree to almost 50 degree. On the other hand, anything beyond this plus or minus 15 degree is reject. That also has been reduced by about 8%. So this has been shown here as the control charts here. So this is within, and this has been this part also been reduced. Another aspect is whenever in a single coil, suppose there is some intermediate portion which is outside this band, okay, and the rest of the coil is good. So we do a kind of reprocessing. We take it to another line, cut and remove the non-compliant part, and again dispatch the remaining coil. So this reprocessing has reduced by by almost 32% between these two successive financial years. These are in tons. Okay. The second thing, a consistent improvement in the fuel efficiency. There is an 8% reduction in the fuel usage, and similar effect on the CO2 emission. Okay. So now, one important aspect of why we decided to take it on ourselves was once we master this technology, this methodology, we can apply it to other plants, okay, other processes within the in the steel manufacturing. The second thing is the retaining the share of the business in the growing market. There is extreme competition in the steel market, the automotive steel market. So we are setting up new plants, and our existing plant efficiency and quality also need to be improved. So we have 2 more plants coming up in our Kalinganagar facility. There also this solution will be going. So this is the last slide. Few second comment from our Vice President, Steel Manufacturing, Mr. Chaitanya
It
Banu.
is challenging to manage any continuous manufacturing line with its inherent complexities. In the annealing line, the dynamic operating environment makes it even more difficult. The operational research-based approach has given us an ideal real-time optimization solution. This is a great change management success story. The improvement in product quality has been phenomenal, with product volumes within the premium band growing by over 30%. Fuel consumption and CO2 emissions have reduced by 8% for every ton of steel which has been processed from this line.
So I'd like to acknowledge some of the colleagues. Mr. Sujit Jagnade had been our lead engineer, technical lead in the project. And these two gentlemen, Mr. Aru and Mr. Sai, had been from the line operation team. Senior management, Mr. Ajay Jha and Anil is the chief of CRM complex, cold rolling mill complex, and Mr. Anil Pujari is the chief of flat product manufacturing. There had been a lot of facilitation and encouragement and support from the senior management, that we must say. And Mr. Kunal Kumar from the research team of Professor Redvardhan of in IIT Bombay. So I'd like to give acknowledgements to them. Thank you. That's all from my side.
Okay. Yeah, I think in the interest of time, we will give the question. I think there are 3 questions which is in the Q&A section. Inderjeet Singh, is he there? Looking at the scheme, do radiant tubes come in an electric version, or do you burn a fuel? It is there in the Q&A session. You can log in. I'm just reading this once again. The question is from
So I heard,
Singh.
Professor.
Okay.
It is we use the fuel burning. We use gaseous fuel, basically cleaned cocoa and gas. The gas generated in the cocoa.
Okay. The second question also you can see. Do you think Gaussian processes can be used for modeling and predicting strip temperature prediction problem?
Yeah, so I can take this question.
Yeah,
we can
Sachin.
use Gaussian processes or neural networks. Gaussian processes would be quite ideal there between complete black box and the kind of models that we have used. Yes, we can use Gaussian processes to predict steel temperature, future predictions. Yeah.
Okay. There is a question from Nitish Umang. What is the time step size in the QP model? Can you please briefly comment on the trade-off between solution accuracy and computational complexity of the QP problem? How is QP solved? In which solver? In a continuous basis? Yeah.
Okay.
Professor Sachin.
So, yeah, I can take this. So right now, it's one QP problem is solved every 1 minute. And this is using MATLAB's QP interior point MATLAB solver. I mean, MATLAB has multiple solvers. MATLAB's QP solution we have used, and it takes fraction of a second to solve this problem. So the problem dimension is of the order of 60 to 80 decision variables. So it's not very high for online implementation. And using MATLAB, it's just so it's for this size of the problem with 1 minute sampling interval, it's really a fraction of a second. It doesn't take much time to solve the problem.
And you stored the previous solution to have for a starting point for the next one. For every minute you are doing
we need to save the previous solution for starting point as a good start. Yeah, that we do, but there is one more solver which we were toying with, which doesn't require that. There's a solver called OSQP, Oxford and Stanford solver. It's a public domain software. So that one, it's managing without that. But yeah, MATLAB solver requires a previous solution as a good guess. Yes.
Good guess. Okay. I think I will open this for questions. Although we have a little bit exceeded the time by 2 minutes. The person who is actually attending would like to have a direct question, I think you are welcome, and we will unmute you.
There are 2 more questions.
Okay, 2 more questions. I didn't see this. One is Professor Sengupta. Okay, Professor Sengupta, can you speak? We can unmute you, or I will just read your. For Dr. JK, how are the temperature positioned from the Sengupta? And for Professor SP, as you have collected a lot of data, how easy, difficult it will be for ML to train a auto control system. Excellent human machine synergy for implementation. Yeah, that is what I figured out. So with Dr. JK and with Professor SP, first Dr. JK and then Professor SP. Yeah.
So the question was how the temperature is measured. I did not get it. Could you please repeat that question?
How are the temperature positioned? For,
So
position means, is it a measurement?
yeah,
I
measured
think Professor
temperatures.
Sengupta. I think let me try to get him if he's around.
If you're talking about measurement, to measure the furnace temperatures, we have got thermocouples inserted at different locations, strategic locations inside the furnace, which gives a representative temperature of each zone. Okay. If you talk, and with respect to strip temperature, at the furnace exit, there are pyrometers, okay, which are properly calibrated, which measures the strip surface temperature continuously. And strip being a thin object, so it's assumed that the temperature is uniform across the thickness of the strip.
Professor
So I hope I
Sengupta, can you
answered it.
unmute? Professor Sengupta, can you
Yeah.
unmute?
I think maybe one of the admins.
Can I answer the second question?
Yeah,
Yeah, I think you can answer. No.
Yeah. So the data collection, yeah, we had to collect a lot of data because there are multiple grades. And what is important is that when you make some change, the plant should show the response. It should get excited. So the data should have sufficient excitation. So collecting data from the historical records, the data which is relevant for modeling, was a challenging task. It was not so easy. Once you have data, yes, you can train ML models to do auto control systems. Yeah, that is the next plan, that we want to use machine learning models like GP or neural nets to develop better models which will model nonlinearity and uncertainty better. Yes.
Okay. There is one
But
more
data
question.
collection is a challenge. It's finding out relevant data from historical records, or doing perturbation trials is very easy, particularly for the running plant. That was very, very difficult.
One question from Manish Kumar BR. How did you convince your operators in trusting your solution? More of a management question, not technical. Yeah.
Yeah, yeah, I will take it. Of course, there is. See, of course, there will be resistance. See, as I said, it's a habit of 20 years, and each one, and it was a new line. Each of those operators grew up in that line. Okay, so they're very proud of their skills, and they're very proud of their, the product that they make. So when you enter, there will be. So that's what I said, that the change management, it needed a lot of strategic approach, as also teamwork also. The strategic approach was like, you don't give us a set point which is not visible to them. Now we are giving the furnace temperature set point, so he is able to see what the solution is suggesting, and he would think what I would have done. Okay, so that way, that they were able to relate to the they were able to appreciate the genuineness, so to say, or the or the correctness of the set point suggestion from the MPC. So they did not see it as something alien and something throwing out something what we say unsuitable recommendation. There was council, teamwork was very much important apart from this.
Yeah, there is no further questions. So anybody from the audience? Still, I think audience size has decreased now. Any question?
I think we should.
I will just add that I found maths was the most easy thing to do. The convincing operator was probably much more difficult. Yeah.
Yes. Okay. I think we are much beyond the time. We think we have exceeded the time over 7 minutes another. So on behalf of Informs and on behalf of ORSI, Rajesh, would like to add anything or before I close?
No, just
No.
thank you to both the
Thank
speakers
you
for
for
this
all. I think
presentation
we
and
had
also
a great attendance today. I think we have over 33 attendance
Yeah.
today. So great thing. I think please continue. And if you are planning to give any talk, let me know or Rajesh know about this. We'll be happy to host a webinar like this. Thank you, Dr. Jose. Thank you, Professor Pattavardhan. I think excellent work which has been done. So please motivate everybody to do similar work in the future. Thank you.
Thank you. Thank you.
Thank you, Beth, also for organizing this in very short time.
Yes, thank you.
Thank you, Sanjay.
Bye. Bye.